There are several considerations for sizing power factor correction capacitor banks. In order to correctly size a capacitor bank, you need to know the load profile, the utility tariff, and the future growth of the operation. Did you know that improper capacitor bank sizing can result in continued utility penalties if the kVAR requirement is not met? That's why today on the Power Grid, we're going to discuss key factors in sizing a power factor correction capacitor bank. Hello and welcome back to the Power Grid, a podcast to help you build reliability in your electrical system and gives you confidence in your power. I'm Brian Brannigan with Power Protection Products. We have been solving power quality problems for almost 30 years. We're your trusted advisor for critical power, cooling, and energy solutions. Capacitor banks come in a variety of sizes, formats, and stages. It's important to get the right capacitor bank installed in the right place with the correct capacity and functionality. Installation location and size are very important when dealing with a capacitor bank project. Capacitor banks have several staging options and tuning features that should be considered for demanding electrical production environments. Heavy industrial users need to understand these changes and how it will impact the electrical system. How much can you save by installing capacitors? Power factor correction capacitors provide many benefits. You can have reduced electrical utility bills, increase your system capacity, improve your voltage, and reduce your losses. Let's start by talking about reducing your utility bill. Your electric utility provides working kilowatts and reactive power, or kVAR, to your plant in the form of apparent power, most commonly referred to as kVA, or kilovolt amps. While reactive power, kVAR, doesn't register on the kW demand or the kW hour meters, the utility's transmission and distribution system must be large enough to provide the total power. Utilities have various ways of passing the expense of larger generators, transformers, cables, switches, and the like along to you. Utilities use a term called a tariff to detail out how your operation will be charged for the utility services. These tariffs can change based on things like your particular service or service size, that's usually called a rate class, or the utility company's need for growth, or the utility company's capacity, or even based on the purchasing of power from the national electric grid. We're going to spend a little bit of time talking about a letter that a utility company might send out to a production facility talking about their tariff and their power factor correction. I have a recent example here that happened in our area where it says the power district rate requires customers with an electrical demand of 300 kilowatts at or near the time of peak demand to maintain a minimum of 90% power factor to avoid billing penalties. The letter goes on to talk about how listed below is the present power factor and kVAR of capacitance needed to correct your power factor to 100%. Increasing your power factor to near 100% will also significantly reduce the kVA load on the transformers that serve your facility and extend the life of your equipment. So the utility goes on to say, please add the capacitance needed for power factor correction to avoid billing penalties, which will be added to your monthly bill starting in January of 2025. Your electrician should be able to help you get the proper equipment needed. And then it goes on to talk about the power factor of that particular facility, which was 82%, And they also copied the rate schedule that particular facility is on. And there are various rate schedules based on the electrical usage of the different facilities. This happens to be on a rate schedule 3. So you'll have to know what sort of rate schedule you're on before you can even make an attempt to correct for power factor. So let's talk a little bit about capacitor bank sizing. Even the most basic questions, like how much capacitance is needed, is not a simple question. Utility power factor penalties vary considerably, and power factor is not calculated consistently from one utility company to another. Several pieces of information is needed. The profile of the existing load, the kVA or the kW, peaks and valleys, the desired target power factor, like a 0.9 or a 0.95, or maybe even in the example I just read, a 0.1. And this is all based on the utility tariff. Another consideration would be the time frame the utility calculated power factor, like 15-minute intervals or 30-minute intervals, or the time frame they calculate the penalty at, like the peak load or over the course of a month. Most utilities calculate power factor on peak demand, but we have seen penalties even in the non-peak demands. I'll give you an example. We were dealing with a utility tariff and a power factor penalty at a welding facility in Kansas. And although we corrected the power factor to 0.95 while it was in production, when everybody went home at the end of the day, or even when they went on break for lunch, there wasn't much of a load on the facility at all, but the power factor was very low because there might have been one or two pieces of equipment on, such as an air compressor motor or something like that, that didn't require the kVAR injection needed to increase the power factor. So basically, at night or when everybody went on break, they had a very bad or very low power factor, and the utility continued to charge them for a low power factor penalty, even though there wasn't a high demand for energy. So we had to go in and fix that capacitor bank to operate both at the high end of the spectrum of peak energy demand and even at the low end of the spectrum when everybody went home for the weekend or for lunch breaks. So once you've decided that your facility can benefit from power factor correction, you'll need to choose the optimum type, size, and number of capacitors for your facility. There are two basic types of capacitor installations: individual capacitors on linear or sinusoidal loads, and banks of fixed or automatically switched capacitors at the feeder or substation. And these typically come in 50 kVAR or 100 kVAR capacitor nest or increments of injecting kVAR. The advantages of individual capacitors at the load are that they can give you complete control, and the capacitors cannot cause problems on the line during the light load conditions. There's no need to separate switching motors, always operate with a capacitor. Improve motor performance due to more efficient power use and reduce the voltage drops. Motors and capacitors can be easily relocated together. It's easier to select the right capacitor for the load if it's a motor load, and you have reduced line losses, and it increased the system capacity. The advantages of a bank installation or a capacitor bank at the service entrance or substation is that it's lower cost per kVAR that you're injecting into the system, and the total plant power factor is improved, and this reduces or can eliminate all forms of kVAR charges on a utility tariff. Automatic switching ensures exact amount of power factor correction and eliminates overcapacitance or leading capacitors and resulting overvoltages. Facilities with large loads benefit from a combination of individual load, group load, and banks of fixed and automatically switched capacitors. It doesn't have to be one or the other. You can have a mixture of both. A small facility, on the other hand, may require only one capacitor at the service entrance. Sometimes only an isolated trouble spot requires power factor correction. This may be the case if your plant has welding machines or induction heaters or DC drives. If a particular feeder serving a low power factor load is corrected, it may raise the overall plant power factor enough that additional capacitors may not be necessary. But it's important to consider the load consistency as well. If your facility operates around the clock and has a constant load demand, then fixed capacitor banks offer the greatest economy. If the load's determined by 8-hour shifts 5 days a week, you'll want more switched units to decrease capacitance during the times of reduced loads. Another thing to consider is the actual load capacity. If your feeders or transformers are overloaded, or if you wish to add additional load to already overloaded lines, correction should be applied at the load. If your facility has surplus amperage, you can install capacitor banks at the main feeders. If load varies a great deal, the automatic switching capacitor bank is probably the best answer. Let's talk about sizing capacitors for the entire plant load. If you know what the total kilowatt consumption of your plant is at its present power factor, and the power factor you're aiming for based on the utility tariff, it's a lot easier to make recommendations for sizing. The sizing will be based on the load profile, the utility tariff, and the actual presence of harmonics. You can always look at the kilowatt, or kW, versus the kVA and calculate the power factor, but the timing of the kVAR stages will also need to be considered based on the operation. Other important considerations are things like harmonic mitigation, the actual capacitor stage coordination, and even the cabinet sizing and the feeder breakers will need to be considered when sizing a capacitor bank. I'll give you an example. We were in one facility once where it had a particular amount of kVAR in the capacitor bank, and there were 3 large gray electrical cabinets. And these cabinets are about the size of a refrigerator, basic kitchen refrigerator. The first cabinet contained capacitors. The second cabinet contained line reactors for harmonic mitigation. And the third cabinet was mostly empty, but it had one nest of line reactors in it. So the sizing of that particular product was a little bit off because we needed a whole extra cabinet for just one nest of line reactors. So when you're looking at sizing capacitor banks, you have to actually look at what you're getting in the cabinet, and filling up the cabinet with capacitors or filling up the cabinet with the corresponding line reactors is a great idea, because these capacitor banks will be injecting typically 50 or 100 kVAR per nest or per stage, and it's a good idea to have some extra stages available. These stages will inject based on a rotating program, so the first stage doesn't start all the time. It rotates through the capacitor bank. So it's a good idea to have some extra capacitor nest in there, or size the capacitor bank a little bit extra so that you're not putting the same pressure on all the equipment all the time. You have a little bit of extra room in there. So you want to make sure that the cabinets are full of equipment and not just open a cabinet door and see one tiny little reactor nest in the bottom of the cabinet. That was basically due to poor sizing. Some of the other mistakes that we've seen on capacitor sizing is things like lack of room for expansion of the capacitor bank. There's particularly coordinated wire and breaker sizing required for installing a capacitor bank. And you want to make sure that if you were to go back in and expand your capacitor bank, perhaps you may not need to increase the wire size or the breaker size if you still have some space available in the actual specifications of the size of breaker. We also see a lot of premature failure due to harmonics. When you buy a capacitor bank with line reactors, you are adding extra equipment, an extra cabinet typically, and a lot of extra cost. But this equipment is going to perform better and last longer because you are addressing the harmonic issues. And we suggest you do that with a power quality study when you're looking at putting capacitors in. There's going to be other issues like the heat issues in the room. These capacitors do put off some heat, and if the room is already hot, you're going to be adding to the heat by the use of the capacitor bank. There's also concerns about having breaker space to be able to feed the capacitor bank. You may want to size your capacitor bank with an integrated breaker if you don't have breaker space in your electrical equipment already. And then the cabinet sizes themselves and the clearance requirements for these cabinet sizes need to be taken into consideration when you're looking at sizing capacitor banks. They have to fit in the room, and they have to have the ability for air to flow around them. Now, P3 has been in the power capacitor business for over 20 years, coordinating power factor correction capacitors used in low voltage and medium voltage applications. We began working with a number of customers to help resolve problems related to capacitors and harmonic distortion. And during that time, we developed a number of designs to incorporate harmonic filtering in both fixed and automatic capacitor banks. And the success of these installations has made P3 the leader in the field of harmonic filters and capacitor bank installation. P3 also provides on-site supervision and startup services to ensure that all the capacitors and harmonic filtering assemblies are properly applied in the plant environment. P3 is dedicated to ensuring that reliable, efficient, and safe power is available when it's needed most. With unparalleled knowledge of electrical power management across a variety of industries, the experts at P3 can deliver a customized, integrated solution to solve your most critical challenges. Our focus is on delivering the right solution for the application. But decision makers demand more than just innovative products. They turn to P3 for an unwavering commitment to personal support that makes customer success a top priority. Thank you for joining us today on the Power Grid. Power factor correction can be a difficult project, and P3 is here to help you with the decision process. A site visit is almost always needed, and learn more by checking out the podcast notes or go to p3-inc.com.